So in the next 20 minutes or so, I'm going to talk to you about a line of research within the field of quantum gravity that does not involve a lot of string theory. The sort of general idea of this line of research is to consider quantum corrections to classical gravity theorems and quantities and sort of observe the interplay between the two and try to find hints towards what a fundamental theory of nature might look like. So it's kind of a bit like playing Sherlock Holmes and looking for footprints of quantum gravity. At least that's what I like to call it. And yeah, that's what we're talking about today. And I've divided this talk into three parts. In the first part, I'm going to sort of motivate a bit where this line of research originated from by talking about black holes and holography. The second part, I'll talk about entropy bounds and the so-called generalized second law of black hole thermodynamics. And in the third part, I'm going to talk about the relation between this generalized second law with something called the quantum focusing conjecture and also the quantum law energy condition. If you don't know what these are, I'm going to explain them later on. Okay. So let's start with the first part. The first thing I wanted to mention very quickly is just a short comment about entropy. So in thermodynamics, entropy is the logarithm of the number of microstates that an observer who looks at a system cannot distinguish. So it sort of measures the ignorance of an observer. And if we have an observer who's sort of maximally ignorant, he can't distinguish any of the microstates, then the entropy would just be the logarithm of the total number of possible microstates that this system can have. And so this is sort of like a fine-grained entropy, and it's the same as the information content of the system, right? Because if the ignorance of the observer is everything there is to know about the system, then this ignorance is equal to the information content of the system. Now this is a classical quantity, but there's also a quantum mechanical sort of analog to this classical quantity. And the question is sort of what do we put in this logarithm? And in quantum mechanics we have Hilbert spaces, and the states or the microstates or microconfigurations of our systems are eigenstates of that Hilbert space. So the number of distinct eigenstates of the Hilbert space would just be the dimensionality of that Hilbert space. And therefore, in quantum mechanics, this fine-grained entropy or the information content of the system would just be the logarithm of the dimensionality of the Hilbert space. One example would be, for example, if you consider a system with 100 spins who can point either up or down, then the dimensionality of the Hilbert space of that system would be 2 to the 100. And if you put this in the logarithm, then you would find that the entropy of the system would be, it depends on which logarithm you choose, but it would be something, let's say we choose the logarithm to the basis 2, then the entropy would just be 100. And you know how spins are, that's sort of like I can point up and down, they're like bits, you know? Zeros and ones. And therefore we can think of this 100 as coming in the units of bits. So in some sense the information content of a system that consists of 100 spins is 100 bits. Okay, so that's one comment I wanted to make about entropy, and now let's talk about black holes. So, as I said before, the concept of entropy, at least in physics, comes from thermodynamics. And I want to do a little analogy here. So let's consider thermodynamics, just take a gas as an example of a thermodynamic system, and on this side we have a black hole. And now, so the macrostate of the gas is sort of very simple. It's described by just a handful of parameters, such as temperature, what else do we have, pressure and volume. And black holes are also very simple. They're described by their mass. If they have a charge, then that's something you can distinguish, and then also angular momentum. So both gas and black holes are very simple objects in the sense that they're described by a small number of parameters. And next thing is, in thermodynamics, there's this law, the second law of thermodynamics, that says the entropy cannot increase with time. So delta S has to be it cannot decrease with time, so delta S has to be bigger or equal to 0. And Hawking showed that black holes, I mean this is nothing to do with entropy, but black holes obey something very similar when it comes to area. The area of a black hole cannot decrease with time, it can only increase. Even when two black holes merge, then the area of the sort of new black hole that results from that merger has to be bigger than the two areas combined before, the sum of the two areas of the original black holes. So this sort of yes, it's a statement about black holes that Hawking showed. And then furthermore, there's this, I think the first law of thermodynamics, which is that the change in total energy is proportional to the change in entropy, and the proportionality constant is the temperature of that system. And again, there's something very similar about black holes, which is that the change in mass, when you throw something into the system, is proportional to the change in area of the black hole, and the proportionality constant is kappa, it's the so-called surface gravity. And again, this sort of looks a little bit similar. And then there's the zeroth second law, the zeroth law of thermodynamics that says that no system can ever be brought down to temperature 0. And well, if you look at this thing here, then it sort of looks like as if this kappa played somewhat a similar role to the temperature here. And indeed, so this cannot be the case. And to create a black hole with, so what's the reason why we cannot bring down the system to zero temperature? This would cost an infinite amount of energy, right? And the same is true here. To produce a black hole with vanishing surface gravity, this would mean that the curvature of the horizon had to vanish. So we would have to make a black hole infinitely large, and this would require an infinite amount of mass, and therefore an infinite amount of energy. So for this sort of the same reason why a system cannot be brought down to 0 temperature, we cannot create a black hole with vanishing surface gravity. So this is interesting. It looks as if the gas and the black hole would behave in a very similar, analogous way. Energy sort of being the analog to mass, temperature being the analog to surface gravity, and even more interesting, maybe entropy being analog to area. And so I'm going to jump ahead a little bit. So, so inspired by this interesting similarity or analogy, Hawking proposed that black holes have entropy, and the entropy of a black hole is proportional to its area. And later on, he showed that the proportionality constant is 4g h bar. Yeah, but this is the entropy. This is the important part, maybe for now. So black holes have area, have entropy, and as we said earlier, entropy quantifies the ignorance of an observer when he looks at something. When he sees less than there is. So the question is, what is there in this case? This suggests that black holes have hidden microstates. So they're not, as general relativity claims, described by just 3 quantities, but they have microstates, and the number of microstates is proportional to the area. And well, for this GH bar is essentially, we can replace this by the Planck length squared, so it's sort of the Planck area that tells us what the resolution of this horizon is. Right. So this is kind of our first footprint of quantum gravity. So I just call this FP1. The first footprint of quantum gravity: black holes have an entropy, because neither of our theories, neither quantum field theory nor general relativity, tells us anything about the microstates of a black hole. If anything, we would need a theory of quantum gravity to say anything about microstates of black holes. So this is our first footprint of quantum gravity, but just considered really gravity and compare it with thermodynamics. Okay, so black holes have entropy, that's interesting. The second thing is, later on Hawking showed that this property here, that the area of black holes cannot decrease, is actually not true. Black holes evaporate. They emit particles and their area decreases. Now this sort of looks like as if this second law of black holes, so this is like this second law of black holes, were violated. But so even if the area of the black hole is the entropy of the black hole, and decreasing the area by Hawking evaporation would decrease the entropy of the black hole, this is not a bad thing as long as the entropy goes somewhere, and as long as the system where the entropy goes to compensates for the loss of entropy, at least exactly, or overcompensates it. So if we consider a black hole, then the sort of solution to this problem is to recognize that a black hole is not an isolated system, not a closed system. When it evaporates, the entropy that it loses gets emitted to the outside world. So it adds to the entropy of the matter fields outside. And the quantity that should really be considered for a second law is not just the horizon of the black hole or the area of the black hole, but it should be the area of the black hole plus the entropy outside. That should be the quantity that shouldn't be able to increase to decrease with time. And so this is called the generalized second law, and it's a statement about the generalized entropy. And the generalized entropy is the area of the black hole plus the entropy of the matter outside. And this is the quantity that should not be able to decrease with time. So this is what's called the generalized second law. I always forget the h bar, so there's always an h bar in the denominator of the entropy. Yes. Okay. So let's talk a little bit about entropy bounds. So the origin of entropy bounds was the spherical entropy bound. And it's the idea that if you have a matter configuration that sits in some, so you pick out some spherical region of space, we call this, I just call this region R, and it has a boundary, and the boundary has an area. So this is sort of the area of this region of space. And there's no particles sitting there, there's a matter configuration there. Now, what we can do is we can throw more particles inside and make this matter configuration denser and denser and denser, still leaving it in sort of confined to this area, to the same area. And eventually it's going to collapse into a black hole. And when it collapses into the black hole, its entropy will be precisely this area. Overflow. Right? So if we believe in the second law of thermodynamics, then before this matter configuration collapsed to the black hole, its entropy cannot have been larger than the area of the surface that confined it, right? Because if it were larger, then collapsing into a black hole would definitely bring it to the area. If it was larger before, then this would violate the second law of thermodynamics. So the entropy of a black hole is really sort of the upper bound on the entropy within a certain region of space. Right? So this is the entropy of within this region of space, and there's no way this can be larger than the area of a black hole. There's no way this can be larger than the entropy of a black hole with this area. If we want the second law to be obeyed during black hole collapse. Alright, so this is an entropy bound. This is a general statement about the number of stuff or the number of degrees of freedom that you can put into any area of space, really, at least an area that's spherical. And it says that the amount of stuff you can put in is bounded by the area of this. Or in other words, the degrees of freedom of a region of space is bounded by the area of this region, which is a bit strange because if we look at quantum field theory, then let's take maybe this spin example again. If we take quantum field theory, we take a lattice, and on every lattice point we have a spin that's sitting there. And let's say we have n spins, and we consider the lattice within some volume V, right? So we have n spins, which means that the dimensionality of our Hilbert space, or quantum field theory Hilbert space, is 2 to the n. And then the entropy would be n log 2 or something. So it's proportional to n. The entropy is proportional to n, and n is just the number of lattice sites in this volume. So n is proportional to the volume. So entropy is proportional to n is proportional to the volume. So entropy is proportional to the volume in quantum field theory. And this is just the statement that degrees of freedom in quantum field theory are local. Right? So every point in space is independent from the other point in space, and they're not correlated in any particular way. Which is why the number of degrees of freedom is extensive. But this entropy bound suggests that that's not the case. When you make your matter configuration denser and denser, eventually the number of degrees of freedom is not extensive anymore. It's going to grow with less than the volume. So I mean this is essentially the idea of holography. That if you have a region of space, so let's draw this region. It's a sphere, and it looks like as if, at least from the quantum field theory, well, effective field theory perspective, I guess, that every point in the sphere is independent of every other point, and the degrees of freedom of the entire sphere is proportional to the volume. But really, what this entropy bound here suggests is that fundamentally, the fundamental degrees of freedoms, which first of all seems to be different than the degrees of freedom of the quantum field theory, the fundamental degrees of freedom, they all fit on the area of this sphere, not on the volume, and that's essentially what the idea of what the word holography entered this field, because you can describe something in a three-dimensional space with degrees of freedom that fit on a two-dimensional space. And we also know the resolution of this two-dimensional space. It's 1 over the Planck length. So you can sort of think of the area of this surface as being tiled by sort of small squares of size of roughly the Planck length squared. And that's the number of bits that you can possibly fit into this volume. Yes. So that's this footprint of congruity. It tells us that the fundamental theory of nature is holographic in that sense. The fundamental theory of nature needs less degrees of freedom than our naive effective description of the world seems to suggest. Alright. So the problem with the spherical entropy bound is that it's not covariant. In fact, the thing that's not covariant is the notion of inside. Right? So the spherical entropy bound says that the entropy of stuff inside a region R is bounded by the area of that region over 4G bar. But it's not obvious in general relativity what it means to be inside a region. And so this sort of screams for a covariant formulation of the entropy bound. And this covariant formulation was done by Raphael Busso in, I think, 1999. And he did formulation of an entropy bound in terms of light sheets. So what he considered again a region R. So this is the region R, and this region R has a boundary B. Okay, and I'm going to draw this a little differently now. I'm going to sort of look at this region from this side. So all we see is the boundary. So this is the boundary. And now what we do is we send non-expanding light rays from this boundary in all directions. Now we could also send light rays in this direction, but they would be expanding. And it turns out that this it's not very useful for defining a notion of insight. So we're not considering these light rays, we're just considering the ones that are non-expanding, which means the ones that sort of go towards the middle. Right, and also at this point they intersect. This is a caustic, and here they will continue, of course. But the reason why we don't continue them there is because this is the point where they become expanding again. So just by saying we shoot out light rays from the boundary of our region that are not expanding, this defines this causal diamond. And it turns out that this definition of, or this notion of insight is a very robust notion, which is useful for defining entropy bounds that are Lorentz invariant. Okay, now so the covariant entropy bound is essentially a statement of so these light rays we shoot up here, they produce a light sheet, right? So this thing is called a light sheet, the whole thing. It's a codimension one hypersurface, null hypersurface, and the statement of the covariant entropy bound is essentially that the entropy flux through the light sheet, the number of stuff that can sort of get in and out, or that can get out, is bounded. So this is the entropy flux that goes through the light sheet between here and here. And this entropy flux is bounded by the area of our original region. So this is bounded by the area of B. Oh, R, yeah. Okay, so this was the original formulation of the covariant entropy bound. That the entropy flux through a light sheet that's constructed in this way by non-expanding light rays that terminate at the caustic. That this is bounded by the area of the region from which you shoot this light rays. And it was later shown, or it turned out, that you can even make a stronger statement than this. Actually, let me draw this here. You can even make a stronger statement than this by not letting the light rays go all the way up, but by sort of terminating them, let's say here. So we shoot them from here to here, and it's always helpful to parameterize this. So we have an affine parameter, we call it lambda, it goes along the null direction, and it parameterizes our light sheet. So we shoot light rays from lambda to lambda, or lambda 0 to lambda 1, let's say. And here we have our original region, and here we have a region that's smaller, right? So it's the region within the light sheet, or within the light rays. Yeah. And again, we can look at the entropy flux that sort of that leaves the inside of this hypersurface between lambda 0 and lambda 1. And this entropy flux, again, is bounded by the change in area from here to here. So this is bounded by A of lambda 0 and A of lambda 1 minus A of lambda 1 divided by 4 G H bar. So it's bounded by delta A. Okay. And now, what's this this entropy flux that leaves the inside region. Where does it go? It goes outside, right? So this is really nothing but the change in entropy of the outside fields, or actually minus the change in entropy of the outside fields. And sort of making this association and rewriting this a little bit, this is nothing but the generalized second law, right? So what we have here is minus S out is bounded from above by the change in area over 4G. And now if we, wait, which side do I want to put this? I want to put it on this side, right? So if I put this on the other side, then I find that the change in area plus the change in outside entropy cannot be smaller than 0. And this is nothing but the generalized second law, which says that, so this is nothing but d, the change of the generalized entropy. And this statement that the change in the generalized entropy cannot be smaller than 0 is the generalized second law. So the generalized second law implies the covariant entropy bound. Okay, now we're back to the generalized second law. Let's continue looking at it for a bit. Because there's something interesting to learn, I think. So the generalized second law, I'll write it down, the generalized entropy, sorry, I write it down again, is the area over 4G plus the outside entropy. And so what is this outside entropy, by the way? How do you calculate it? In quantum field theory, it is the von Neumann entropy, right? So we have a global density matrix. So let me just draw this for a moment. So this is a conformal diagram of Minkowski space. You take a Cauchy slice, and you take some radius. This is your region R, and you call this inside. This is outside. And you have a state rho that lives on the entire Cauchy slice. It's a global state. And now the entropy of the outside fields would be minus the trace of, so you trace over the inside degrees of freedom, so that you're only left with the outside ones, and then rho log rho. Right? So this is a von Neumann entropy with the inside degrees of freedom traced out. That's what's meant by S out. And so if you actually calculate this, you will see that this entropy diverges, and the divergent part of this entropy is proportional to the area of your region. And the reason for that is because of short distance entanglement. So if you have one global state, or in quantum field theory in general, if you have a global state, so we divide it into two parts. This inside, this is outside. And what you find is, if you sort of look very closely, you see that if you look at a two-point function of let's say, field operators here and here. If you bring these field operators closer together, you see that the two-point function diverges. This has to do with short distance entanglement of quantum field theory. It's another way of saying this is that the Hilbert space of quantum field theory never factorizes. It's a fact about quantum field theory. So you have this entanglement structure of the degrees of freedom, and so this is entangled with this, and entangled with this, and so on. There's no way of sort of truly separating the degrees of freedom by just drawing a line in space. And so if you calculate this S out, what you find is a divergent piece that's proportional to the area, and of course, so if it diverges, you need some kind of momentum cutoff. So it's proportional to the area over the momentum cutoff, and then you have some subunit pieces that are logarithmic, and I won't get into these, they're very important. The important thing is that it's really this divergent piece here. Because with this divergent piece, the generalized entropy has two area terms now. One area term comes from the black hole part, or the original area part, and then the second term comes from the outside entropy, which is also to leading order proportion to the area. And then there's these subleading terms. And the interesting thing to learn here is that that this term is the first counter term of the RG flow of the Newton constant. Right? So the Newton constant has a non-trivial RG flow, and it turns out that this is precisely the counter term of this, which means you can sort of absorb the first term of the entropy of the outside entropy. You can absorb this into G. Now, the outside entropy is a purely quantum field theoretical concept or quantity, and it turns out that it's the same as the RG flow of a gravity quantity, namely the Newton constant. Right, so you can write this as you can absorb the divergent part of the outside entropy into the renormalization of the Newton constant, and you find that this generalized second law, because of this interplay here, the generalized entropy is much better defined than both the entropy outside and the area by itself. And that's the second footprint that I wanted to point out. The first one being, I already raised it, the black holes of entropy. So this suggests that there is a non-trivial interplay between quantum mechanical quantities really and classical gravity quantities that were really sort of they're not. You really have to do some work to see this. So this is sort of the one of the results of being a Sherlock Holmes. And, right. Okay. Okay. Let's now play with the generalized entropy a little bit more. And playing with it more is going to lead us to the concept of a quantum-corrected area. So the generalized entropy, as you see it here, I forgot the H bar. One thing we can do to this is we can multiply everything by 4g H bar. So let's just do that for a moment, just for fun. So 4g H bar times the generalized entropy is the area. Or if I didn't write this, but to be very precise, this area is the expectation value of the area, right? Because if you include quantum mechanical corrections, then these quantum mechanical corrections sort of do small deformations around the surface that you define. And what we really mean when we write area is the expectation value of that surface that sort of averages over the quantum coefficients for the quantum fluctuations. So just from now on, I think I'm going to write this. So the generalized entropy times 4gh bar is this expectation value of the area plus 4g h bar of the outside entropy. And so this is quite interesting. The first term has no h bar in it, right? So this is h bar to 0th order, and this has an h bar. This has one h bar in it. So it kind of looks like as if the generalized entropy multiplied by this factor is nothing but an area with the first quantum correction already included. So this is right. So this is nothing but the quantum corrected. This is nothing but the quantum corrected area of the region that we're considering. This thing here being the first order quantum correction in an h bar expansion. Okay, so now, just from the generalized second law, we have a quantum corrected area, and now we can try to do something with this and see how we get it. So one quantum mechanical theorem that includes areas is the focusing theorem. The focusing theorem says that if you have two light rays, and you put some matter here, then these light rays will always focus. They're not going to anti-focus. And essentially this is a statement about matter about energy densities always being positive. And one way of making this statement explicit is by saying that the expectation value of the stress energy tensor is always bigger than 0. In this case, it's the stress energy tensor along the null direction because we're considering light rays here. So from the point of view of a null observer, of an observer who goes with the light rays, energy densities always look positive, and that's why light rays always focus in classical general relativity. Okay, but now, yes, okay, so the focusing theorem of general relativity just says that the area spanned by these light rays can only decrease but not increase. Or that, no, not the area, the rate of change of that area, right? And the way this is written is by, so we have this, I'm not going to talk about this very much. We have this expansion scalar, and the first derivative of with respect to a fine parameter that parameterizes your light sheet. The first derivative of this is smaller equal than 0. Okay, so this is the classical focusing theorem, which states that the area spanned by light rays, the rate of change of the area spanned by light rays can only decrease. And yes, assuming, so this statement only holds if we assume this. It's called the null energy condition. So any restriction on the stress energy tensor is an energy condition, and in this case, because it's along the null direction, it's called the null energy condition. And yeah, I mean, so we can maybe I just mention this very briefly. So this expansion scalar essentially is determined by the Riko equation, which looks like this. And yeah, from this we can already see that this is only smaller or equivalent to 0. So this is the first derivative with respect to this affine parameter lambda. It's the same as this. And this is only smaller or equal to 0 if the expectation value of the stress energy tensor is positive or 0. So that's why we need the null energy condition to make this statement. Okay. So classical focusing is a statement about areas of light sheets. So it's a statement about areas. And we just said that the generalized entropy gives us a quantum corrected area. So one thing we could try is we could, instead of just considering the classical area of the light sheets, we could consider quantum corrections to this area and see if the focusing theorem still holds. One thing we know is that the null energy condition doesn't hold. If we include quantum corrections, we can in fact have negative energy densities locally, and this would violate the null energy condition. If the null energy condition is violated, then the classical focusing theorem can also be, the classical focusing theorem can also be violated, right? So let's try this. Let's instead of the classical area consider the quantum corrected area that we got from the generalized entropy, and see if we can see if this is still the case, and if not, if we violate the classical focusing theorem. Let's see what we can do to save it. Let's see if there is a quantum generalization of this focusing theorem. So the reason why we might be looking for this is because what we found is that the generalized entropy is much better defined than the two entropies that went into it. And maybe we find something similar here. Maybe we find that something like a quantum focusing theorem is in some sense much better defined than the classical focusing theorem. For example, because the area is better defined. So, and also because it's robust against quantum fluctuations, which is important sort of on the path to quantum gravity, because eventually there will be quantum fluctuations, and ignoring them is sort of a little bit naive, at least when you're working in the field of quantum gravity. Okay, so instead of the classical expansion scalar, we promote this to a quantum expansion scalar. I call it big theta, and we can work this out. We can sort of do things to the rational dual equations. I'm not going to do this in detail here because we don't have much time left. But essentially, it's just the classical expansion scalar plus 4gh bar over this infinitesimal line area times the first derivative of the outside entropy and this probably the second derivative times the expansion scalar. So this is our quantum expansion scalar, and now we conjecture that this expansion scalar obeys something similar to here. That the rate of change of the quantum, the rate of change of, so instead of this area, this infinitesimal area element being a classical area element, now it's a quantum area element. And what we want to propose, or what we conjecture, is that this cannot be positive. So that's our quantum focusing conjecture. And it's still a conjecture, but one thing is interesting about this. So we said that including quantum corrections violates the null energy condition, because locally we can have, even to a null observer, we can have negative energy densities. So the null energy condition is not the energy condition that goes into this, but in fact no energy condition went into this, because all we did is we replaced the classical area with the quantum corrected area and conjectured this, right? And so now we're going the other way around and seeing, we can now ask, after having conjectured this, what energy condition, what constraint in the stress energy tensor from the point of view of a null observer results from this. And if we do that, what we find is the following energy condition that results from this. And it turns out that it's bounded by the second derivative of the outside entropy that's proportional to it. So we replace the classical area with the quantum corrected area. By doing that, we define a quantum expansion scalar, and we conjecture that this expansion scalar, analogously to the classical expansion scalar, obeys this condition. We call it the quantum focusing condition, or the quantum focusing theorem. It's only conjecture. We conjecture this, and we ask what constraint on the stress energy tensor, like the null energy condition for the classical case, what condition on the stress energy tensor results from this. And what we find is this energy condition, and it's again along the null direction, but this certainly includes an h bar. So this is sort of the quantum null energy condition, the QNEC. And this is interesting. So the QNEC, it has an h bar, but it doesn't have a g, right? So this is a statement purely about quantum field theory. It's not a statement about gravity, but we got it from starting with the gravity theorem, right? So we started with the classical focusing theorem, which is a purely GR concept. It involves areas and how these areas change with some fine parameter. We started with this. We included small quantum corrections to the area that we're considering. Found out that this is no longer true because the null energy condition is no longer true. We defined this, this quantum expansion scalar, conjectured that that this quantum expansion scalar obeys this condition, sort of saving the concept of a focusing theorem, but now a quantum generalized version of it. We found, as a result, this energy condition, which does not involve gravity anymore. So we learned something about quantum field theory, starting from a classical gravity theorem. So this is the third and last footprint of quantum gravity. So the fact that this is possible, the fact that we can learn something about quantum field theory by studying quantum corrections to classical gravity, tells us that there is an interesting, or that there's some non-trivial interplay going on between the two theories that may hint towards a fundamental theory of quantum gravity. So this is the third footprint sort of that we identified in this talk. And so I want to, in the last 5 minutes or so, I just want to summarize a little bit and make some final remarks, and then that's it. Okay. So I want to finish this talk by just drawing this interplay again that we found. So we have the classical focusing theorem, and into this classical focusing theorem goes the null energy condition. And we also have something called the second law of black hole thermodynamics. And it turns out that classical focusing is really the same as the second law. That you can, turn them into each other. And now, so this is sort of at the level of h bar equals 0. And now we go to h bar equals 1 and see which of these concepts we can generalize, we can quantum generalize, or we can make robust to leading order quantum corrections, which is what this entire talk was sort of about. When we do this to the second law, we get the generalized second law. Generalized second law being a statement about the generalized entropy, and the generalized entropy, as we've seen, is just sort of a quantum corrected version of the area. So first order quantum corrections, we get the generalized second law from the second law, and then we've seen that the generalized second law we turn the generalized entropy into the quantum corrected area. And what we get from this is the quantum focusing conjecture. In fact, we can show that if we take h bar to 0, the quantum focusing conjecture reduces to the classical focusing conjecture. And we found that the energy condition that went into this quantum focusing conjecture is the quantum null energy condition, which is a new statement about quantum field theory that was not known before. And again, we find that we take this quantum null energy condition, we take h bar to 0, it reduces to the null energy condition of classical gravity. So it really seems that these the things up here, the generalized second law, the quantum focusing conjecture, and the QNEC, they can really be thought of as quantum generalizations of these classical theorems, and sort of each of them taught us something about quantum gravity, possibly. Right? So this was the statement that black holes have entropy, and the generalized entropy, so if the entropy of the black hole plus the entropy of the matter outside is much better defined than either of the entropies together. That was our first footprint. The first thing that we learned about quantum gravity, that there's an interplay that makes quantities better defined by cancelling, by divergences cancelling. Well, this is always the case, right? In effective field theory, when we have divergences, these divergences are usually due to new physics that is not described by our theory. So every time when divergences cancel, we sort of have the feeling that we're getting closer to the full picture. And this was one of the cases where divergence cancelled, where we could absorb the divergent part of the outside entropy into the RG flow of the Newton's constant, and they cancel precisely. And well, the third footprint was that this quantity here is a quantity, a purely quantum field theoretical quantity that we simply got from, we started here, we did this, so we started with the classical focusing theorem, we included quantum corrections, and we ended up at, so this is a GR theorem, we included quantum corrections, and we ended up at a theorem, at a statement solely about QFC that involved absolutely no Newton's constant, only h bar. Yes. My last sentence for today, I think a lot can be learned from this interplay between classical gravity quantities and theorems and their quantum corrections. Because in a fundamental theory of nature, there should really be the same degrees of freedom. And the things we've seen today in this talk, or the things that this line of research has sort of brought to the surface, is that this interplay is really non-trivial and leads to very interesting results, such as things being better defined, divergence cancelling, new statements about quantum field theory that come from classical general relativity, and so on. So this hints towards these degrees of freedom, the quantum mechanical degrees of freedom, and the classical GR degrees of freedom sort of being complementary in some sense, or eventually even being the same. Yeah, I think I'm just going to stop here and take questions now if there are any. Thank you.